So let's get into it. The most important question I think you have to ask of anything you want to propose to NASA, especially at wavelengths that are accessible from the ground, like the ones we're doing for BEX, is, why do we need a space instrument? Um, and in the EHT context, we can very easily make the case that what we were able to see, what we are able to see with EHT, what we could see with NGHT, is transformationally different from what was possible for decades at 3 mm wavelength, just because we went to a wavelength of 1 mm. It made our resolution almost 3 times higher, and it pushed us further into the synchrotron fog around these, our two prize black holes and other jet sources that have appeared in talks in the last day and a half. And that meant we could do very different things than what had come before. In the case of BEX, we know EHT has reached to the maximum extent of the size of the Earth. It has very nearly reached to the atmospheric frequency limits that the Earth imposes upon us. And when we talk about the science of the photon ring and the really detailed studies of jet and horizon scale sources, we need higher resolution. So at a very minimum, we have to push off the Earth in order to make our array bigger. And we, in a couple slides, I'll go through some quantitative aspects of that, but we need to make BEX achieve resolution a few times higher than what we can do from the ground. And so if we're going to have to go to space in order to access the very different science that we could do if we could get at the photon ring at few microarc second resolution, we have a lot of new challenges because you can only make something in space so big, and so your sensitivity is limited. And so we have to push very hard to get the sensitivity we need to be able to get significant detections of correlated light between the ground and space. In order to do that, we need to digitize a lot of signal bandwidth. That's normally an energy-intensive process, handling all those bits. And then, in our case, more importantly, download those to the Earth where we could do some correlation. And, space VLBI missions have existed before. The most recent, Radioastron, flew hydrogen masers, which are large and heavy, because you have to preserve coherent wavefronts in space and on the ground with a very precise clock. And so we need to do that at a higher frequency than ever before. And that's a tricky ask. So, in detail, what do we have to do? How high in frequency do we have to go? The design of BEX is driven, we looked at the science, all of our science cases, and we looked at all the requirements that they impose on us. And the most stringent ones come from the primary targets, the ones you think of as our obvious goals, Sagittarius Star and M87. If you look at what frequency we have to get to in order to see down to the event horizon, and you explore a variety of models, you can see in the figure at the top left that we need to get to about 200 gigahertz for M87 to be confident that we're seeing down to the innermost regions. And in Sagittarius Star, maybe it's 300 gigahertz. Obviously we do it at 230 with EHT. But the problem with Sagittarius Star is that when we're going to higher resolution, we're subject to the limits imposed by the interstellar scattering that happens between us and the galactic center. And that means we need to push to above 300 gigahertz. And so the BEX instrument is designed around the idea that we're going to do space VLBI at a frequency of above 300 gigahertz. In order to get the resolution we want to get sort of 6 microarc second, 7 microarc second resolution, we're talking about sort of 30 gigalambda baselines. That is sufficient for us to be in the region of the visibility domain, as shown in the figure on the right, where we are primarily seeing the photon ring. A neat trick of interferometry is that because we're observing the Fourier transform of the sky, even though the photon ring is buried in a mess of mostly unlensed or weakly lensed emission, because it's a sharp feature, it stands out above that emission at long baselines. And so the long baselines are critical to us. And when we started looking at this, an orbit of approximately 12 hours is sufficient to do this and has other nice features for us to get good UV coverage over the course of half a day. In order for this to work, we also need to be sensitive enough. We have the advantage in very long baseline interferometry that the sensitivity, the RMS noise on a given measurement between two telescopes depends on the geometric mean of the area of those two telescopes. So if we can have large telescopes on the ground, and we can with things like ALMA, LMT, the Plateau to Bureau Interferometer, NOEMA, then we can have a large thing to multiply by the biggest thing we can fit in a fairing. That has pushed us to about 3.5 meters. I'll get to that in a second. We also need to have very sensitive receivers up in space. We need to gather the widest bandwidth we can. And our ground stations have to be at the best sites we can find on the ground. Fortunately, because we're using, millimeter, submillimeter facilities, that's already been true. These facilities are preferentially at sites with good weather, with very little water. And so as long as we can involve enough of those in our observations, we should be able to achieve the, few millijansky sensitivities that we need to be confident that we'll see visibilities, detect correlated light between space and ground. If we weren't sensitive enough, there's a real risk, not one I think we face, but there's a real risk. You take lots of data and just never find significant detection of real correlated light in all the noise that buries your signal when you're doing VLBI. Timing coherence with the ground. So I think when I started thinking about space VLBI seriously, I mean, people have been thinking about this for a long time, but I hadn't been thinking about it very seriously. I had enough to do on the ground. The question that concerned me most was the question of coherence. It's the first or second question I get asked about this almost every time I talk about it. Because, you imagine VLBI, you've got a plane wave coming from a source and it's hitting one antenna, and then some other time it's hitting another antenna. And those antennas are far enough apart, even if they're not in space, that they do not share any oscillator. And so they are to digitize that electric field on your antenna and play it back and multiply it against the other one, you have to have an extremely precise reference source to perform that down conversion and digitization. And if you don't, you will just wash away the correlation and you won't see the signal you want, or you'll reduce the amplitude of it and change the answers. For the space clocks, we are pretty confident that there are ultra-stable quartz oscillators that are space ready, or already in space, one already on its way to Jupiter, that are suitable for our coherence needs. They are good enough to get us to 300 gigahertz without causing an appreciable loss of signal. Another tricky thing, though, is that when you're looking at these high frequencies, the atmosphere can cause a wiggle that's bigger than these very good clocks. And so we had to find a way to get around that. Because in order to detect correlated light between space and ground, we need to coherently integrate for not just a few seconds, not just maybe the 30 seconds the atmosphere would allow, but minutes. And so the way we are pursuing that is so-called frequency phase transfer, where we observe simultaneously in two bands at once. If we observe at a longer wavelength where the atmospheric perturbation is smaller, 3 times smaller in the case of our setup, we can measure the atmospheric induced phase between space and ground. We can scale it up by a factor of 3, and we can subtract it out of our data. You can see an example of this in the figure at right, where we've done these tests. Sarah's online, and she's been leading with Don Pesci the effort to demonstrate this at EHT and GHT BHEX frequencies. And this shows that the phase as measured from an 86 gigahertz system scaled up by 2.5, matching pretty well with the 215 gigahertz, helping us remove the atmosphere. So BHEX is designed to do exactly this, and this gives us confidence that we will be able to detect this coherent light, remove the problems that the atmosphere cause, and get our visibilities. The instrument itself looks like this. This is a rendering from the preparations we're doing for the proposal. We have 3 subsystems in this thing. We collect the light with an antenna. We receive the light with a state-of-the-art dual band, dual polarization receiver, and we digitize, process, and downlink the data with what we call DIPI-BIRD, the wow, digital processing. Huh. Janice, help me. Why can't I think of our acronym right now? This is
Because
not
it's
good.
complicated.
It
Petabyte,
is.
infrared.
Yeah, that's right.
I forgot what the D was. But
Yeah.
but but it harkens to T-Bird, which is the instrument that flew beforehand, which is
Yeah.
important. And so, but we probably have made this too complicated if we can't even pass our own quiz here.
Well, it's 9 a.m. for me, so excuse, I apologize. Anyway, Don talked about that yesterday in the evening session, T-Bird, I mean. So those are our 3 subsystems. We are making a lot of progress on this, right? So, we started by defining the uh, requirements of the system and figuring out how we are going to meet those requirements. And we have been pushing forward the engineering of this system ever since. I mean, we thought we had a deadline of last summer to get a proposal together. So that really motivated a lot of effort to put this all together and to make it work and to make it viable. So, at the front end, we after the antenna, we have the coherent receivers. We are really pushing this wide bandwidth downlink. There's lots of pieces that go into this, but almost everything that's on here is stuff that people have used before. We have used before extensively on the ground. People have used before in space in many cases. And so we're focused on demonstrating that all of this is technically ready in the closest configuration possible to exactly what we want to fly. So for example, the antenna, I actually really love the antenna. It's a carbon fiber reflector working with Airbus. They have another funded space mission that is helping drive this in their own priorities and sort of in parallel with us. It's a little bit ahead of us. They previously, before they were incorporated under Airbus, but at the same facility, built uh, the mirrors for the Planck mission. Planck observed up to 1 terahertz, which places much more stringent requirements on the surface quality than we have. We're pretty confident that they can achieve the surface quality we need. But to prove it, as part of demonstrating this is all working, we're working with them to measure, very carefully characterize a half-scale version of the antenna in advance of the proposal. And a neat thing about this design is, we have this powerful instrument team behind the instrument, and we have an antenna designer for NRAO who was working on the NGVLA and has brought us this antenna design that's far better than I'm used to in the submillimeter, where we're using greater than 90% of the aperture across the whole band. Just getting from the more typical 65 to 70% to 90% is of great benefit to us. And we wouldn't have done that without such a high quality antenna designer in Robert Lemonsey. The receiver. So, as I said, it's a dual band receiver. To achieve our sensitivity goals, we need to use the best 300 gigahertz receiver we can, which means using superconductor, insulator, superconductor mixers. These are near the quantum limit. They have to operate, unfortunately, at 4.5 Kelvin. And, if you were on last night at the end, Ranking Homa gave an overview of BHEX Japan. The Japanese contribution to this instrument is absolutely critical to this being viable. Space qualified cryocoolers are not easy to come by and they're not cheap, but they have one that is unimpeachably ready to do what we need to do. It's working right now in CRISM, and it meets our specs exactly. And so we just need to build another one and put it on this thing. Our tunings are designed to observe in two frequencies at once, scaled by an exact ratio of 3. The low frequency receiver covers 8 gigahertz instantaneously, and if you scale that up by a factor of 3, it perfectly straddles the 24 gigahertz span of the high frequency receiver. And so we can just take the phase we measure in the average of this band and subtract it out of these bands to do the frequency phase transfer. The rough frequency coverage is here. The details vary slightly from this, mostly giving us more frequency coverage. And each receiver gives us 2 polarizations, 8 gigahertz wide, double sideband in the case of the high frequency receiver, and single high or upper or lower sideband for the low frequency receiver. Part of ensuring coherence in the system is metrology. Once this thing's up in space, we will have a hard time knowing that it is behaving stably. We will test it on the ground, but it's trust but verify in this case. And so a thing that we want to be able to do is inject a coherent signal into both bands simultaneously, something that's generated from the same frequency reference, and compare that phase of that signal in the 2 bands to measure the time delay between them and make sure it's not changing. We have now demonstrated this. Gabriella Montano is a finishing senior at Northeastern, and she spent the spring and summer working with Edward Tong in the receiver lab and came out to Kitt Peak to work with me and test this thing out on a 1 millimeter and 3 millimeter receiver simultaneously. You can see our beautiful comb with all these spikes in it that we will be able to correlate between bands. It works really well, and so this part is ready. We're also about to test prototype SIS mixers. Mareki actually showed test data from NAOJ where they were made yesterday, and in November they'll be at SAO under test in fully assembled state. The back end system requires us to handle an enormous amount of data. We have a space qualified FPGA at the heart of this. We have space qualified digitizers ahead of that. The analog signal processing that we need to do ahead of it has been prototyped and built. You can see a picture at the upper left and upper right of this space component based board. It worked as intended. We'll do some vibration testing and environmental testing, and that will be TRL6 and ready to go. We're working through the firmware on the FPGA. We're getting ready to do a test with Lincoln Labs on their optical test range, where we actually relay information through an optical link and record it in collaboration with MIT Haystack also. When this all works, and we expect it will, we'll make it work, we will be delivering 500 times the data rate of Radio Astron. And so, it is hard to scale up by a factor of 10 in frequency in space VLBI. But as far as your ability to detect the signal goes, having a 500 times increase in data rate and therefore a 20-time increase in sensitivity is a good start. So as I mentioned before, Don did summarize the state of space optical communication. It is a rapidly growing industry. It's quietly on Starlink satellites, and more startups are coming into the space. If we have to submit the proposal right now, we have a ground scheme that will allow us to receive these data all over the world, we think. But this is like the old story about just wait a little bit to buy your computer stuff or buy it at the last minute. The longer we get to wait before we have to say what our plan is in the proposal, the better the optical ground station system will look. On the space side, we're just buying a commercial off-the-shelf space laser terminal, basically, because this is getting common enough that we can do that. Finally, we have confidence we can do this. Both SAO and Arizona have a great deal of space history. This is an example of University of Arizona space history. We have done a lot of big things. The big ones that are happening right now is OSIRIS-REx and now OSIRIS-APEX. It's post sample return mission are led out of here. JWST instrument was built in our building, and another one, the instrument scientist, is in our building. The Marsha Riki's PI of NIRCam, and George Riki is the instrument scientist on MIRI. And so, these are recent. Aspera is a Pioneers mission that's almost ready for launch, just waiting for the government to be normal. So there's a lot of big stuff. The same goes for SAO, which, is responsible for IRAC and Chandra and or the Chandra X-ray Center, and Tempo currently up there, an instrument on Parker Solar Probe, many other things. So we think we can carry this out. We think we have lots of people around who know how to do this. Janice knows how to do this. I am learning, and we'll pull it off. I think that's it. I would just show our incredible instrument team, and we can take questions.
Thank you, Dan and Janice. I see Gary has a question.
Yeah,
Knows how to do this.
and I apologize if this was discussed last night and I missed part of last night's presentation. But one notices that the antenna has no sunshade around it in all the renderings I've seen. Has there been a thermal model of the antenna to verify that at the various viewing angles one anticipates that it doesn't cause any distortion in the figure of the antenna?
Great.
Hey,
Yeah,
Dan,
that's a
can I
great
take that
question, Gary.
question? Yeah.
What's that, Janice?
I was gonna say, can I take that, Dan?
Yeah, sure, go ahead.
Sure. So Gary, and just and for everybody, the class of this mission that we're proposing for is called the Small Explorer class, and it has a certain cost cap to it. And we are going to fly a cryogenic system in space at this price point, and we will be the first mission to do that. And so there are other engineering compromises that we have to make. And so what we've done is we've downsized a sunshade to be a thermal shroud. And it's when you look at the picture of the BHEX instrument, you can kind of see the shroud architecture in place. It's been kind of removed, so you can see the inside where the receiver is. And yes, there has been a thermal model. And Gary, while your question is about all solar incidences, I think basically right now at this point in time, we've looked at the min-max sort of cases. And as we go through the mission life cycle, we will continue to iterate that thermal model and make adjustments and things like that.
I would
Dan,
just
do you
add
have
that,
anything to add?
yeah, Airbus did a study of this for us. It was remarkable how robust the antenna was to the variations we would expect. I mean, it's carbon fiber, so it should be thermally stable inherently, but this was less of a problem than I feared it might be. We never let sun hit the dish. The secondary sits below the edge of the dish, so it's relatively thermally stable anyway, but the print through the sun through the shroud is not sufficient to make an important difference in the antenna shape.